In 1999, a research ship drilling into the seafloor off the coast of Northern California made a navigational error. Instead of sampling sediment from the fault system scientists were actually there to study, they drifted 55 miles off course and pulled up a core from an entirely different fault altogether. Most people would have called that a wasted trip. One marine geologist kept the sample anyway. It sat there for years. And when scientists finally went back and looked at what that mistake had actually captured, it cracked open a discovery that has quietly rewritten what worst-case scenario means for tens of millions of people living across the American West Coast. Today, we're breaking down exactly what researchers just confirmed about the Cascadia Subduction Zone, why the fault most people call the big one might not even be the worst thing that could happen, and what a newly discovered connection to California's most famous fault line means for the region's future. Here's what makes this discovery genuinely different from the usual steady drip of earthquake research headlines. This isn't a study refining exactly how big Cascadia's next earthquake might be, or exactly when it might strike. It's a study suggesting the entire mental model most people, including most experts, have used for decades to think about West Coast earthquake risk may have been missing an entire dimension of the problem. Not a bigger single earthquake. Two of them, hundreds of miles apart, arriving close enough together in time that, for emergency response purposes, they might as well be one event. Let's start with the fault everyone already knows something about, because you need to understand its scale before the new discovery actually makes sense. The Cascadia Subduction Zone runs roughly 700 miles along the Pacific Northwest coastline, from northern Vancouver Island in British Columbia down through Washington and Oregon into northern California. It's the boundary where the Juan de Fuca and Gorda plates are being forced beneath the much larger North American plate. And it is fully capable of producing an earthquake at the absolute top end of the scale, magnitude 9 or greater, on par with the most powerful earthquakes ever recorded anywhere on the planet. The last time this fault ruptured along its full length was the night of January 26, 1700. An event scientists have dated with remarkable precision by cross-referencing evidence of sudden coastal subsidence in the Pacific Northwest against Japanese historical records describing a tsunami that arrived with no local earthquake to explain it, having traveled silently across the entire Pacific Ocean roughly 10 hours after the Cascadia rupture actually occurred. Cascadia produces a major earthquake somewhere in the range of every 300 to 500 years. Which means the region currently sits more than 3 centuries into a waiting period that geological history says isn't permanent. Current seismic hazard modeling projects somewhere between a 16 and 22% chance of a Cascadia-wide earthquake reaching magnitude 8, 7 or greater striking within the next 50 years, and the odds of a smaller partial rupture are considerably higher still, with researchers projecting a 42% chance in that same 50-year window of at least a magnitude 7. 4. Earthquake occurring somewhere along a portion of the fault. This is the version of Cascadia risk most people who've heard of the big one are already at least somewhat familiar with. A genuinely catastrophic but geographically contained disaster scenario centered on the Pacific Northwest. Here's where the story most people know gets a lot more complicated, and it starts with that navigational mistake back in 1999. Chris Goldfinger, a marine geologist at Oregon State University, had been part of a research expedition specifically tasked with drilling sediment cores along the Cascadia Subduction Zone, extracting long cylindrical samples of seafloor material that preserve a detailed layer-by-layer record of past earthquakes, stretching back thousands of years. Each time a large earthquake strikes offshore, the violent shaking triggers underwater landslides that deposit a distinct sediment layer, called a turbidite, on the ocean floor, and by carefully dating and counting these layers, scientists can reconstruct a remarkably precise timeline of a fault's past rupture history, even for earthquakes that happened centuries before anyone was around to measure them directly. On this particular trip, a navigational error sent the research vessel roughly 55 miles south of Cape Mendocino in California, planting them squarely within the territory of the northern San Andreas fault system, rather than the Cascadia zone they'd meant to sample. Rather than discard what looked like an off-target sample, Goldfinger held onto the core. It would be years before anyone circled back to examine exactly what that accidental detour had actually captured. When Goldfinger and an international team of researchers finally did return to that sample, alongside a much broader collection of sediment cores gathered from both fault systems over more than 2 decades, spanning roughly 3,100 years of continuous geological history, they made a discovery that fundamentally changes how scientists have to think about West Coast earthquake risk. Comparing the turbidite layers deposited by Cascadia earthquakes against the turbidite layers deposited by earthquakes on the northern San Andreas fault, the team found that a meaningful number of these deposits had formed at strikingly similar times and carried strikingly similar structural characteristics, evidence pointing toward a genuinely startling conclusion. Earthquakes on the Cascadia Subduction Zone appear capable of directly triggering earthquakes on the San Andreas fault system, not years or decades apart, but within minutes to hours of each other. The findings, published September 29, 2025, in the peer-reviewed journal Geosphere, identified at least 3 documented instances over the past 1,500 years where seismic activity between these two fault systems appears to have occurred within that same tight window, minutes to hours apart, rather than as 2 entirely unrelated independently timed events. The most recent of these 3 instances lines up with the historically documented 1700 Cascadia earthquake itself, suggesting that the same catastrophic night that sent a tsunami racing across the Pacific toward Japan may have also triggered a significant rupture on the San Andreas fault system in California, occurring in such close succession that, geologically speaking, the 2 events would have registered as functionally simultaneous. It's worth understanding just how much painstaking, unglamorous work sits behind a discovery like this, because comparing sediment layers from 2 entirely different fault systems, separated by hundreds of miles of open ocean, is nowhere near as simple as lining up 2 timelines and looking for matches. Turbidite layers have to be individually dated using a combination of radiocarbon analysis of organic material trapped within the sediment and careful correlation with known historical earthquakes and other independently dated geological markers. Distinguishing a turbidite triggered by actual earthquake shaking from one triggered by an unrelated underwater landslide. Storm activity or sediment overloading requires detailed analysis of the layer's internal structure and composition. Multiplying that painstaking process across 3,100 years of accumulated sediment, pulled from cores gathered at multiple sites along 2 separate faulting systems, represents years of dedicated laboratory work, which is part of why this specific connection between Cascadia and the San Andreas sat undiscovered for so long, even though the raw sediment evidence had technically been sitting in storage since that off-course 1999 expedition first pulled it up from the seafloor. This is precisely the discovery that should force a genuine recalibration of how people think about West Coast earthquake risk. And Goldfinger himself put it about as bluntly as a scientist can. We're used to hearing the big one, Cascadia, being described as this singular, catastrophic, huge thing, he said. It turns out it's not the worst-case scenario. That's a genuinely remarkable statement coming from the researcher most responsible for building the modern scientific understanding of Cascadia's hazard in the first place. And it's worth sitting with exactly why he's saying it. For decades, the working assumption among both scientists and the general public has been that a full-length Cascadia rupture represents the ceiling of what the West Coast needs to prepare for, an already almost unimaginably destructive scenario on its own. This new research suggests that ceiling may actually have a trapdoor in it, a scenario where Cascadia doesn't just devastate the Pacific Northwest independently, but simultaneously sets off a major rupture hundreds of miles south, in one of the most densely populated regions in the entire country. To understand how one earthquake could possibly trigger another across such a significant distance, and with such a short delay, it helps to understand the actual mechanics of what's called dynamic triggering, a phenomenon seismologists have documented, though rarely, in a handful of other locations around the world. When a major fault ruptures, it doesn't just shake the ground near its epicenter. It sends seismic waves radiating outward through the Earth's crust, and in specific circumstances, when those waves pass through another fault system that's already sitting close to its own failure threshold, the added stress and shaking can be enough to tip that second fault into rupturing as well, even at a considerable distance from the original earthquake. This isn't a hypothetical mechanism invented to explain the Cascadia-San Andreas sediment pattern. It has been documented before, most notably during the catastrophic 2004 Sumatra-Andaman earthquake, and the related activity that continued across the same region into 2005, an event so powerful that American seismologists were able to trace subtle triggered seismic responses in fault systems as far away as Colorado, thousands of miles from the original Indonesian epicenter. Prior to the Goldfinger team's research, the 2004-2005 Sumatra sequence stood as essentially the only well-documented example anywhere in the world of this kind of cross-fault, rapid succession triggering between 2 genuinely major independent fault systems. The new Cascadia San Andreas findings would represent only the second such documented case in the global scientific record, which is exactly why this discovery has generated so much attention within the seismological community specifically, beyond just the obvious public alarm around West Coast earthquake risk generally. It's worth being precise about what this research does and doesn't actually claim, because the distinction matters enormously for understanding the real scope of the new risk. The study doesn't suggest that every future Cascadia earthquake will automatically trigger a San Andreas rupture. And researchers are explicit that pinpointing the exact timing relationship between these 2 fault systems remains genuinely difficult work, given that the underlying evidence comes from sediment layers that can only be dated with a certain degree of precision, not from direct instrumental recordings of 2 earthquakes happening in real time. What the research does establish is that this kind of triggering has happened before, at least a handful of times over the past 15 centuries, including possibly during the most recent, best documented full Cascadia rupture in 1700, and that the underlying physical mechanism connecting the two fault systems is genuinely plausible and consistent with dynamic triggering documented elsewhere in the world. In other words, this isn't a certainty baked into every future Cascadia earthquake. It's a newly confirmed possibility, one that hadn't previously been part of the standard hazard planning conversation for the West Coast, and one serious enough that emergency planners now have to factor it into how they think about the absolute upper bound of what a Cascadia rupture could actually unleash. It's worth pausing on the northern San Andreas Fault itself for a moment, because it's easy to let the Cascadia half of this story dominate the conversation when the southern half carries its own independently massive stakes. The northern San Andreas is the exact fault segment responsible for the 1906 San Francisco earthquake, an estimated magnitude 7. 9 event that, combined with the fires that followed, killed roughly 3,000 people and remains one of the most destructive natural disasters in American history more than a century later. That segment of the fault runs directly through one of the most densely populated, economically significant metropolitan regions in the entire country, home to Silicon Valley, the Port of Oakland, and a Bay Area population numbering in the millions. A scenario where this exact fault segment ruptures within hours of a full Cascadia event isn't simply layering one disaster on top of an unrelated one. It's potentially compounding 2 of the most consequential seismic hazards on the entire West Coast into a single overlapping crisis window with California's own emergency response. Infrastructure, the very resources a badly damaged Pacific Northwest might otherwise have leaned on for mutual aid, simultaneously overwhelmed by its own catastrophic event, just as those resources would be most needed. The practical consequences of that upper bound scenario are genuinely staggering to consider, and Goldfinger laid them out directly in the university's announcement of the findings. An earthquake on either fault system alone, he noted, would already be significant enough to draw down the emergency response resources of the entire country to manage it. If both faults ruptured together in the kind of compressed time frame the sediment evidence suggests is physically possible, the result wouldn't be one regional disaster requiring a coordinated national response. It would potentially be 4 separate major metropolitan areas, San Francisco, Portland, Seattle, and Vancouver, all thrown into a genuine emergency situation simultaneously, each one competing for the exact same finite pool of emergency personnel, equipment, mutual aid agreements, and federal disaster response resources that a single major earthquake would already stretch to its absolute limit on its own. This is precisely the scenario that transforms an already catastrophic, well-understood hazard into something meaningfully harder to plan for, because virtually every layer of disaster response planning, from FEMA's regional resource allocation to individual state mutual aid agreements between neighboring jurisdictions, generally assumes that a disaster of this scale striking one region leaves the rest of the country's emergency infrastructure available to help. A synchronized Cascadia San Andreas event would strip away that underlying assumption almost entirely. It's also worth understanding that dynamic triggering across this specific distance and this specific delay window remains genuinely rare in the broader global earthquake record, which is exactly why researchers are treating this Cascadia-San Andreas connection as such a significant finding, rather than an expected, unremarkable result. Seismologists have documented countless cases of smaller, more localized triggering, one fault segment setting off a nearby segment along the same broader system within seconds or minutes, a phenomenon well understood and routinely factored into hazard models. What remains exceptionally uncommon is triggering between 2 entirely separate, independently mapped major fault systems, separated by hundreds of miles of intervening crust and ocean, occurring within a delay window short enough to functionally count as a single compound disaster, rather than 2 unrelated earthquakes that merely happened within the same general era. That rarity is precisely why the 2004-2005 Sumatra sequence stood alone in the scientific literature for so long, and why finding a second, geologically documented example sitting in North America's own backyard represents such a genuinely significant addition to the global understanding of how major fault systems can interact across large distances. This research didn't emerge in a vacuum, and it's worth understanding the broader context of state-level policy response that was already underway even before Goldfinger's specific findings were published. In early September 2025, just weeks before the Geosphere study came out, Oregon Governor Tina Kotek issued an executive order specifically overhauling the state's approach to seismic building safety, driven by growing concern about Cascadia's overall hazard profile. The order directed state agencies to immediately begin earthquake-proofing any new state buildings larger than 10,000 square feet, and to retrofit existing state agency buildings on a timeline running through 2060, pending funding approval from the Oregon legislature. Goldfinger himself was directly involved in informing that policy response. issuing a statement through the governor's office describing a magnitude 8 to 9 earthquake in the region's future as inevitable, and specifically emphasizing that seismically sound state buildings would be absolutely crucial when that earthquake eventually arrives. Oregon's Capitol building itself has already been the subject of a $598 million seismic retrofitting project specifically undertaken to bring the building up to a standard capable of surviving a major Cascadia event, a concrete, expensive illustration of exactly how seriously state government has already begun treating this underlying hazard, even before this newest research on cross-fault triggering became public. The timing here matters enormously because it shows this new discovery landing directly on top of an already active, well-funded push toward earthquake preparedness across the region, rather than introducing a brand new concern into a policy vacuum. Regional earthquake experts convening throughout 2026 have continued pushing for exactly the kind of expanded coordination and investment this new triggering research would seem to demand, emphasizing that effective Cascadia preparedness increasingly can't be treated as a purely state-by-state or even purely West Coast problem, given that a worst-case synchronized rupture scenario would require resource coordination stretching across international borders between the United States and Canada and across the entire length of the Pacific coastline from Northern California to British Columbia simultaneously. It's also worth understanding how this discovery fits alongside other recent advances in Cascadia research, because the overall picture scientists are building of this fault system has become considerably more detailed, and in several respects considerably more concerning, over just the past few years. Separate research using advanced seismic imaging techniques has produced what researchers describe as an unprecedentedly detailed map of the Cascadia Subduction Zone's actual physical structure, confirming that the fault isn't one smooth, uniform surface, but is instead segmented by smaller horizontal faults cutting through both the upper and lower tectonic plates involved. That segmentation matters directly for earthquake severity because in any given rupture, the number of these individual segments that fail together determines how large an area gets affected and how powerful the resulting earthquake actually becomes, with more segments failing simultaneously translating directly into a larger, more catastrophic event. That same detailed mapping work identified specific sections of the fault where the two tectonic plates meet along an unusually smooth, flat boundary, a geometric detail that actually increases the amount of direct contact area between the plates, making those specific segments more likely to produce especially powerful shaking when they do eventually rupture. Layer the newly confirmed Cascadia San Andreas triggering risk on top of this increasingly detailed, increasingly complex picture of the fault's internal segmentation, and you get a genuinely sobering cumulative scientific picture. This isn't simply a story about one large fault capable of one large earthquake. It's a story about an intricately segmented subduction zone, capable of rupturing in configurations that range from partial, contained events to a full-length, magnitude 9+ rupture, that may also be capable, under specific conditions that have already occurred at least a few times in the past 1,500 years, of reaching out and triggering an entirely separate major fault system hundreds of miles to the south within a matter of hours. So what should residents across the Pacific Northwest and Northern California actually take away from this newly confirmed research beyond simple alarm? The most important takeaway is precisely the one Goldfinger himself has emphasized in every public statement connected to these findings, that this discovery should function as a genuine catalyst for expanded, better coordinated preparedness investment, not as a reason for fatalistic resignation. The kind of infrastructure hardening already underway in Oregon, seismic retrofitting of critical government buildings, updated building codes for new construction, represents exactly the type of concrete, actionable response this research is meant to inform. Understanding that a worst-case scenario might now genuinely include simultaneous emergencies across 4 major metropolitan areas rather than one contained. Regional disaster gives emergency planners a more complete, more accurate picture to actually plan resource allocation against, rather than continuing to operate under an outdated assumption that badly underestimates just how large a coordinated response might eventually need to be. None of this new research changes the fundamental, unavoidable reality that earthquake prediction, in the sense of naming an exact date, remains genuinely beyond current scientific capability for Cascadia, for the San Andreas, or for any fault system anywhere in the world. What it does change is the scientific community's understanding of the true range of what's physically possible when this fault system eventually does rupture again, expanding the outer edge of the worst-case scenario in a way that carries direct, serious implications for how 4 major West Coast cities, spanning 2 countries, ultimately need to think about coordinating their emergency response planning going forward. That's the real story behind this newly confirmed research, 25-year-old navigational mistake that sat quietly in storage until the right team finally circled back to examine what it had actually captured, revealing that 2 of the most dangerous fault systems in North America may be capable of acting in far closer concert than anyone previously understood. The big one was already the standard by which West Coast disaster planning measured its absolute worst-case scenario. Scientists have now confirmed it might not be the ceiling at all, but rather the opening act of something considerably larger, a potential twin disaster spanning San Francisco, Portland, Seattle, and Vancouver, all unfolding within the same compressed, brutal window of time. Stay with this channel because we'll keep tracking every new study emerging from this research. And this is exactly the kind of story where a 25-year-old mistake ended up reshaping how scientists think about the single most consequential earthquake risk in the United States.